Hello everyone, I am Angelos and today I will be presenting IRIS, an interference and resource-aware predictive inference serving system for cloud infrastructures. Over the last years, we observe an ever-increased interest in machine learning, deep learning, and artificial intelligence in general. This figure shows that the AI market size has doubled from 2021 to 2023 and is expected to increase tenfold by 2030. The introduction of AI in different domains such as healthcare, finance, and transportation has led to complex models that require lots of compute, memory, and storage resources to operate. The GPT-3 model, for example, which is the core of the well-known ChatGPT, has more than 175 billion parameters. As the required resources skyrocket, it becomes prohibitive for the end users to support inference. Cloud comes to alleviate this resource wall challenge by taking a significant amount of the computational burden, providing scalable, flexible, and cost-effective solutions. As a matter of fact, inference takes 90% of the total infrastructure cost in AWS, while Facebook serves tens of trillions inference tasks a day. To ease the deployment of inference workloads, cloud providers offer machine learning solutions as services over their infrastructure. With ML as a service, end users can provide pre-trained models along with throughput, latency, quality of service requirements. Typical examples include Amazon SageMaker, Azure Machine Learning, IBM Watson, and Google's Vertex AI. From the cloud provider's point of view, providing such services is not an easy task due to various challenges. First of all, resource interference. Providers tend to collocate applications on the same physical server to increase the resource utilization of their infrastructures. However, this leads to interference in the shared resource of the system, which is translated to high performance variability and quality of service violations. The diversity in quality of service requirements is also a serious challenge, as for example, automotive applications require millisecond scale inference, while agricultural ones can be tolerant to performance variability. Finally, there exists a vast amount of different deep neural network architectures or different versions of the same architecture for performing the same task. These variants trade performance for accuracy and vice versa. Thus, cloud providers must take these challenges into consideration to build inference serving systems that guarantee the user-defined quality of service requirements and maximize resource efficiency. Here we present our experimental setup. We deploy two virtual machines that serve as the master and the worker of a Kubernetes cluster. The master node is equipped with 4 virtual CPUs and 8 GB of RAM, while the worker with 8 virtual CPUs and 16 GB of RAM. For the inference engine workload, we use inference engines from the MLPerf Inference Benchmark Suite. We focus on image classification and object detection inference engines. Finally, we generate synthetic interference using iBench, which contains micro-benchmarks for stressing the CPU, L2 and L3 cache, and memory bandwidth and capacity. As a first step, we tried to gain insight regarding the impact of various parameters to the performance of the examined MLPerf inference engines. These parameters are the different model representation backends, and in our case, TensorFlow and ONNX Runtime. Vertical and horizontal scaling. Vertical scaling defines the number of available thread pools used for parallel executions. It enables operation-level parallelism. For example, internal parallelization of TensorFlow's matrix multiplication operation. Horizontal scaling defines the amount of worker threads that can serve inference requests simultaneously. It is instantiated using Python's threading library and run as background daemons that serve requests from a task queue in a first-come, first-served manner. Interference also to illustrate the effects of resource contention when different shared resources are stressed. So, our first question was, how do different model variants for the same task behave in terms of performance? The number of threads refers to vertical scaling, while the number of workers refers to horizontal scaling. The depicted values refer to the achieved QPS. We focus on image classification task when the number of threads and workers are equal to 1. Different models for the same task have different performance. For example, TensorFlow MobileNet achieves 4.6 times higher QPS than TensorFlow ResNet 50. Another interesting observation is that there is no clear dominance of TensorFlow over ONNX runtime and vice versa. For example, TensorFlow ResNet achieves less QPS than ONNX ResNet 50, while ONNX MobileNet achieves less QPS compared to TensorFlow MobileNet. So how does vertical scaling of resources affect performance? We can see that increasing the number of threads leads to an increase in performance. By increasing the number of threads to 8, we can achieve 2.8 times higher QPS on average for ONNX runtime and 3.8 times higher QPS on average for TensorFlow. As for the horizontal scaling, for TensorFlow backend, increasing the number of workers does not provide performance improvements due to CPython's global interpreter lock. GIL ensures that only one thread is running in the interpreter at a time, and it is designed to simplify low-level details such as synchronization or concurrent threads. It also leads to high single-threaded performance but limits parallel or multi-threaded execution of Python code. ONNX runtime does not benefit also from increasing the number of workers, leading to 14% QPS drop on average. How does resource interference affect the performance of the inference engines? As we expect, increasing the number of I-bands leads to greater QPS degradation. Stressing the CPU and memory bandwidth have the greatest influence on the QPS achieved. In particular, when using 16 I-bands jobs, 11.7 times lower QPS is achieved when stressing CPU, while when stressing memory bandwidth, 12.5 lower QPS is achieved on average. So, do different backends reveal different performance sensitivity with respect to resource interference? As we previously showed, there is no clear dominance of one backend over the other. For example, focusing on CPU stressing with one I-band job, we can see that ONNX ResNet 50 achieves 1.5 higher QPS than TensorFlow ResNet 50, while on the other hand, TensorFlow SSD MobileNet achieves 2.5 times higher QPS than ONNX SSD MobileNet. Finally, how do different resource allocations affect the performance of the inference engines under the presence of interference? For the examined backends, we present the queries per second distributions when stressing different shared resources for different interference level. For the ONNX runtime, the best performance is observed for number of threads equal to 2 or 4. For TensorFlow, the highest QPS values are generally found when the number of threads exceeds 5. The lowest performance variability is observed when TensorFlow threads are equal to 1, And finally, stressing memory capacity has the lowest performance variability compared to stressing other shared resources. Based on our observations, we designed IRIS, an interference and resource-aware predictive orchestration system. IRIS identifies interference effects by exploiting low-level performance events, provides accurate performance predictions, and automatically applies horizontal and vertical scaling policies and chooses the appropriate model variant. IRIS consists of two distinct phases, the online and offline phase. This step concerns the generation of representative collocation scenarios which cover low and high intensity interference across different layers of the system. Each scenario consists of initially deploying a random number of high-bench jobs, each of which occupies a randomly selected resource of the cluster, for example CPU or memory bandwidth. Then we randomly select one of the available inference engines and deploy it with a random parallelism level. To capture the interference effects, we exploit low-level system performance events such as IPC and cache misses, as well as higher-level metrics such as CPU and memory utilization. Finally, we capture the QPS achieved, since IRIS should be able to forecast the future QPS of the inference engines under dynamically altered interference effect. This information allows us to form the dataset for model training. We test various regression models. After evaluating each and every one of them, we end up with extreme gradient boost model. XGBoost model is then fine-tuned, resulting in the QPS prediction mechanism utilized by IRIS. In the online phase, the end user specifies the ML task, i.e. image classification and object detection, as well as the target QoS. Through continuous monitoring, IRIS gains insight into the current level of disruption using the aforementioned system metrics. For the test dataset, we identify the inference engines of the required task. For each inference engine, IRIS predicts the achieved QPS for different parallelism level under the current interference level. Then it performs sorting based on the CPU utilization and selects the inference engine with the parallelism level that satisfies the quality of service with the minimum CPU resources. We evaluate IRIS approach using different interference scenarios of varying intensity, different quality of service constraints per inference engine, and we compare the modelless version of IRIS with all the different interference-aware model-specific IRIS schedulers. For the image classification task, we show the quality of service violation and average CPU utilization of the modelless version of IRIS, as well as the model-specific schedulers. IRIS achieves 57.6 less quality of service violations on average, while it is able to keep the CPU utilization on 21.3% on average. We also present the achieved QPS distributions for all the schedulers. The modelless version of IRIS has similar performance variability with the baselines and manages to keep the QPS value above the quality of service constraint. It achieves 1.2 and 1.6 times higher QPS for low, medium, and high QoS constraints on average. As for the object detection task, IRIS achieves 23.9 less quality of service violations on average compared to model-specific schedulers and a CPU utilization of 34.2% on average. As for the achieved QPS distributions, the modelless version of IRIS has similar performance variability with a baseline and manages to keep the QPS value above the quality of service constraint. It achieves 1.4, 1.8, and 1.5 times higher QPS for low, medium, and high quality of service constraints on average. To conclude, we presented IRIS, an interference and resource-aware predictive scheduling framework for ML inference serving, which guarantees the application-specific quality of service constraints while minimizing resource utilization. The modulus feature of IRIS achieves 1.5 times fewer violations on average compared to model-specific schedulers and 30% less CPU utilization on average also compared to the model-specific schedulers. Thank you very much for your attention.